Morning session. It's a pleasure to introduce Katrin Wendland of Trinity College Dublin, who will tell us about the complex elliptic genera of simple surface singularities.
All right, good morning, Brazil, and thank you so much to the organizers for inviting me to speak. And I should have been in Brazil right now. I'm really sorry I didn't manage to do that. But I'm happy to speak to you here from Dublin now. And the topic of my talk is essentially the results of my PhD student, Yuhang Ho's PhD thesis. So that's him here. And the project I gave him was indeed to make sense of the elliptic genera of simple surface singularities. As many of you know, elliptic genera are nice invariants of manifolds, complex elliptic genera for complex manifolds, but a priori they're actually defined on compact manifolds, while the surface singularities are modeled on non-compact spaces. So it is really a non-trivial question to ask how to make sense of elliptic genera there. And well, he found solutions, or we found solutions to these questions. And the background question I have is, how does this fit into what we know about the elliptic genera and about the VOAs that are associated to surfaces which carry such singularities? So that's the question I have in the background, and I will get to that a little bit into the talk. Now, here's the plan of the talk. Many of you have heard me speak about complex elliptic genera and elliptic genera in CFT as well, but I do have to start by introducing the background and giving you the definitions. So that's what I'm going to begin with. Then I will turn to describing the kinds of singularities that are of interest here. The easiest way to describe them is via quotient constructions. So these are all orbifold singularities that enjoy an ADE classification. Part 3 then will contain the main results, where I'll explain to you how we can make sense of elliptic genera in this non-compact situation and how that fits to what we know, for instance, about the K3 elliptic genus. And then at the end, this is, well, for me, it was the most fun of the project, but it's maybe just the icing on the cake, or a reality check. We found some relations between different types of singularities here, and the explanation of where these relations come from is actually that we can quotient singularities by further symmetry groups and then get to new singularities. So there's quite a pretty formula arising from that, I think. Okay, so let's get to the basics. What is the complex elliptic genus? Well, here we're, as I said, working on a compact, complex manifold in general. Its holomorphic tangent bundle will be relevant later on. It's called T. And for me, the easiest approach to these genera is to start with the Euler characteristic, the traditional Euler characteristic of your manifold. And you can calculate it by calculating the dimensions of certain cohomology groups. So here, HKJ, that's just the dimension of cohomology. I'm using Dolbeault cohomology, and K is the holomorphic form degree, while J is the anti-holomorphic form degree. And then, of course, I have to dress it up again with these signs. That gives you the usual definition of the Euler characteristic, and at the end of the day has the consequence that we're constructing a invariant for the manifold M. Now I'm rewriting things in slightly more convenient ways. For example, I'm noticing that the summation over J here, the summation over J together with the minus signs that are introduced here, the independence of J, actually are just writing out the holomorphic Euler characteristic of this bundle here, the kth exterior power of the dual of the holomorphic tangent bundle. So here I'm just rewriting things in a slightly more convenient way because I've reduced the double sum to simple sum. And then here I'm introducing some notation which will make our life easier later on. That's actually linked to notation that is a little more general, where we're working with these so-called virtual bundles, which on the face of it are just formal power series. X is our formal variable here, and the coefficients are just any bundles. For me, it will always be holomorphic vector bundles, but you could take any bundles. And this notation here just means the direct sum of all the exterior powers of your bundle E, and you keep them apart by distinguishing them by writing this variable in front. And it is legal to insert, say, an integer instead of the variable, and that's what we've done here. We've inserted -1, and this is where that notation comes from. So really, we're looking at the holomorphic Euler characteristic here of the virtual bundle lambda -1 T star. And more generally, we will use similar notation later on for not just including exterior powers, but also symmetric powers. So that's the notation I'm giving you here. That'll occur later on. Okay, so now we have the Euler characteristic written out in many ways. And as a matter of fact, well, it's an invariant of these manifolds. And actually, we're listing more invariants here already. Every single one of these holomorphic Euler characteristics is an invariant. And that might motivate you to introduce something that keeps track of all of these invariants separately, because the way we're doing it now, we're actually just adding them up with the signs, but we would be interested in each of them separately. So that can be done by just introducing a formal variable, keeping them apart. And traditionally, we do that by replacing the -1 here by a -y, and then you get to the Hilsebruch-Kai Y genus. One can, of course, say this in much nicer words. We're actually introducing a C-star action on homology, where the forms with holomorphic form degree k have weight k, and then here I'm introducing an equivariant version of the Euler characteristic, keeping track of that C-star action by introducing the y to the k here. So you see, here's y to the k times -1 to the k, replacing the -1 to the k that we had up there. And using the nice notation that I reminded you of earlier, this is actually nothing but the holomorphic Euler characteristic of a slightly more complicated virtual bundle, where here we're using the -y instead of the -1 over there. And chi is just, I mean, with this notation here, we're just saying chi is supposed to have the properties of a homomorphism. Okay, for later use, it will be useful to know that these Euler characteristics all are given by indices of certain Dirac operators. And because that is so, we can calculate them not just by adding these dimensions here and subtracting these dimensions, we can actually calculate them by means of the Hilsebruch-Riemann-Roch formula. And very roughly, that means that there's a prescription to calculate them through an integral taken over the underlying manifold. Remember, we've required it to be compact, so no trouble here. And then I have to know what to put under the integral sign, when these are the prescribed characteristic classes that you need to use there. And from here, it's not that far anymore to introduce the complex elliptic genus. The idea is that we've already introduced an interesting invariant here, where we're taking the holomorphic Euler characteristic of that virtual bundle. And I'm just going to make that virtual bundle much more complicated now. And it remains visible, actually, in the definition, where for the complex elliptic genus, we replace that bundle by this one here. And you see this classical lambda minus y t star is still hidden in there. We're just dressing it up with further decorations. This prefactor here doesn't have to bother us at this point, but what's more interesting is this infinite product here, where I'm attaching exterior powers of the cotangent bundle, exterior powers of the tangent bundle, symmetric powers of the cotangent bundle, and symmetric powers of the tangent bundle. And of course, a priori, this comes out of nowhere. I think it's important to know that the motivation here really came from string theory, where one tries to generalize this idea of having a holomorphic Euler characteristic over here. And now, instead of working with the usual Dirac operator, I would like to work with the Dirac operator on the loop space of M. That's terribly ill-defined. You get infinities right away, but one way to get rid of infinities is to introduce equivariant notions. And what one is doing here is introducing a U1 equivariant version of the elliptic gene, of the holomorphic Euler characteristic for such a Dirac operator on the loop space. And you can see that equivariance taken care of by the parameter Q here. Q actually is measuring keeping track or introducing the equivariance with respect to the U1 action, where on the loop space, you're rotating the loops just by a U1. And that's what Qn is marking out. N tells you that you've rotated n times. And I think I'm not going to go into further detail here, although this is very, very interesting, but one can actually trace every single ingredient here to that idea of working on the loop space, just that you still have to regularize things and you have to make it U1 equivariant for things to be well-defined a priori. That you can also just view this as a formal definition where, okay, we agree that this is a nice virtual bundle and we're going to consider the holomorphic Euler characteristic of that, where you should read this in the sense that I try to explain here. Chi is a homomorphism, so you can pull the sum sign in front and you can pull all the formal parameters in front. And at the end of the day, you're just calculating holomorphic Euler characteristics of slightly weird holomorphic bundles. And of course, this had a very good motivation, and therefore what you construct here actually is a very nice invariant. It's an invariant of this manifold M. And it's well defined not just as a formal power series in Q and in Y, but as a function, a holomorphic function in parameters tau and Z, where Q is e to the 2 pi I tau and Y is e to the 2 pi I Z, just the way you're probably used to it. And not only that, it has modular properties in the cases that we're interested in. So actually you've, with this definition, you've defined something quite beautiful and useful. So here are some of the properties. I already said this. The complex elliptic genus arises from a regularized U1 equivariant index of a Dirac operator on the loop space, although one should say much more about this to make it precise, but that's the motivation behind the definition. And then to see the modular invariance, the technical tool that makes that visible best is to use the splitting principle. And that says that you can, it's legal to decompose the total Chern class of your bundle here into factors like so, where the xj are the so-called Chern roots. And you can use the xj to these xj to express every single one of the characteristic classes that we did our integral over. So everything can be expressed in terms of the xj, and that makes life much easier. And here I'm doing that explicitly under the integral. I'm writing out the known forms of the characteristic classes in terms of the xj. So what's read here is the classical part. You have the Todd genus and the Chern character of that classical bundle we started out with when we were still discussing the Hiltzeburg-Chi-Y genus. And then here, and this infinite product, you see the contributions from all the other stuff that I told you corresponds to going to loop space. And probably I should have said it then already. It's fun to introduce Q equal to 0 at some point. You will see that everything then collapses back to where we started. It collapses back to the Hiltzeburg-Chi-Y genus, apart from this little decoration that I wrote in front of everything, and I didn't justify that yet. But I'm going to do that now because the expert, of course, has observed already that under the integral now I have produced theta functions. I've actually produced a quotient of two Jacobi theta functions. And that only works because of the prefactor here. And with that information, it's maybe not too surprising when I tell you that this construction gives you something with nice modular properties. We're going to see modularity with respect to the full modular group, but of course we have to be a little bit careful because these parameters here also have to be transformed. And that's why modularity doesn't hold in full generality. I was working with arbitrary complex compact manifolds. So far, it only works, if you do the calculation, it only works when the first Chern class vanishes. And formally that translates into the sum of all the xj to vanish. And when you have that, then you can manipulate this integral and check that actually what you have is a weak Jacobi form of weight 0 and index d half. So that's really pretty. And well, okay, we have an invariant of these manifolds, complex compact manifolds with vanishing first Chern class. We like to call them Calabi-Yau manifolds. And now the beauty of this is also that there really is a partner of this construction in conformal field theory. And again, I'm going to be quite quick here in telling you what my assumptions are, so we actually get to where I want to get. But I mean, these elliptic genera show up in two-dimensional superconformal field theories just as well. So in the following, C will be a two-dimensional superconformal field theory. We will need the supersymmetry, actually quite a lot of supersymmetry. We need n=2 supersymmetry on the left and on the right as well. And in addition, we need space-time supersymmetry. Also, I will require that the central charge, which will be equal on the left and on the right, is an integral multiple of 3. Positive integral multiple of 3. Well, then such superconformal field theories exist. Actually, a lot of them exist. We have families of such superconformal field theories. That's why it makes sense to ask about invariance for these superconformal field theories. Of course, as every quantum field theory, we have a space of states. Here, I'm going to restrict my attention to the Neveu-Schwarz sector, so roughly half of the space of states. And that's legal because I said space-time supersymmetry. So all the stuff that I'm not listing here now is completely determined in terms of the Neveu-Schwarz sector. And well, of the huge superconformal algebra that we have acting here, I won't need all of it, actually we'll need just a little bit of it. And these 4 operators that I've listed for you here will actually be the only ones that we will be using. So these are the 0 modes, both on the left and on the right. On the left, I'm not decorating them. On the right, I'm decorating them with a twiddle. These are the 0 modes of the U1 currents and the Virasoro field, and actually I'm using a kind of a twisted version, topologically twisted version. It's just this linear combination here. Okay, so definitely these act on the Neveu-Schwarz sector, and a little bit more because I said space-time supersymmetry, and actually the space-time supersymmetry always extends our n=2 superconformal algebra. We will only need the holomorphic part of that, so I'm calling it A. A contains J0 and L0 and the entire n=2 superconformal algebra, and a little bit more because of the space-time supersymmetry. For example, if D is equal to 2, and that's the case I usually work in, if D is equal to 2, then the extension is just from n=2 to n=4. But in other dimensions, it's a little less elegant. So that's what we have here. Okay, now we're lucky we're only after this elliptic genus, and for calculating the elliptic genus, actually we do not need all of this Neveu-Schwarz sector. It is sufficient to work on the so-called topologically twisted or topologically half-twisted model, and that's just fancy language for reducing our attention to the kernel of this operator, L0 twiddle top. So that's the topologically twisted Virasoro here. That is still always an infinite dimensional space. It carries a representation of all the operators that I listed for you here. So in particular, these 4, and A acts as well. So that's fine. And just as a matter of fact, we see that later on, instead of using this huge space here, we can restrict our attention to this much smaller space when we want to construct what will be the elliptic genus. Well, if this kernel is so interesting, by the way, in physics, these are called, the elements of this kernel are called BPS states. So here we have quarter and half BPS states. Well, if this is so interesting, why don't we also set L0 top to 0? So we are intersecting the kernel of that guy with the kernel of L0 top. Of course, you can do that. That's also useful. The result will always be a finite dimensional space. So maybe things are a little bit too easy here, but let's start playing with this guy first. It's always a finite dimensional space, and one can indeed construct invariants for these types of conformal field theories from just the information given in this finite dimensional space. It turns out that this is a useful combination. Well, if you believe me that this is a finite dimensional space, then certainly we're just adding a finite number of +1s and -1s. So we're getting some integer and it's well defined. It turns out that at this point, it is useful to rewrite the definition of this funny invariant, which by the way is called the Witten index, to rewrite the Witten index in a slightly more complicated form, I'm smuggling in these two operators. Seems to be useless on the first side, because if L0 top and L0 tilde top are both 0, which I've imposed here, then I've just multiplied by 1. But careful, I've changed the space which I'm taking the trace over. I'm now taking the full topologically twisted H0 tilde, or that's what the brackets mean here. I could also take all of the NS sector, and it really doesn't make a difference. That is an effect of supersymmetry. That is an effect of supersymmetry. The worldsheet supersymmetry that I've required up there leads to a situation where, for example, here, when we're looking at any contribution from an eigenvector of L0 tilde top with positive eigenvalue, that guy will have super partners that contribute with the very same eigenvalues of this guy and this guy, but with the opposite signs here. So the contributions will cancel. And that means that when I write it out like this, with or without the brackets, everything that doesn't come from the kernel of this guy and the kernel of this guy does cancel out. So this is a real the correct equality sign here. Okay, so that's the Witten index. We now can push it a little bit further, or can try to interpret what I just said. The point is that actually here already the geometric interpretations may enter. The expectation is, although there's not even a start of a proof for this, that whenever your superconformal field theory is given by a nonlinear sigma model on some Calabi-Yau manifold, then that finite dimensional space that we had up here, that finite dimensional space actually models the homology of your manifold. And that would immediately explain why the Witten index here is an interesting invariant, because then we're just taking a decorated sum of dimensions of cohomology, and we've seen that before. It actually turns out to be just the Euler characteristic, because indeed also the bigrading which we have on this space through the eigenvalues of J0 and J0 tilde translates into the bigrading that we have on this space through the holomorphic and anti-holomorphic form degree. So if that equality of the vector spaces holds, then the equality of the invariance follows. So Witten index is just another word for Euler characteristic if we're in this situation with the nonlinear sigma models. That's the expectation. And because of this identification here, we can easily push it just one step further. We can introduce the Hirzebruch-Chi-Y genus now as something that we can read off from the representation content of our superconformal field theory. We will continue to work on this space here. And we're just replacing the -1 to the J0 by -y to the J0, just the same way we did it on the first transparency in the geometric context. Okay, and now one step further even, one can now introduce in this setting a definition of a conformal field theoretic elliptic genus, where similarly one does expect that the conformal field theoretic elliptic genus agrees with the complex elliptic genus of your underlying manifold, which I introduced previously. And to define the conformal field theoretic elliptic genus, we use some of the motivation I gave up there. We're using the very same operator to take the trace of, but instead of restricting to this finite dimensional space here, we're going to work on the topologically half-twisted model. So we're changing the space which we're taking the trace of. So that's then the definition of the conformal field theoretic elliptic genus. As promised, we're taking that operator which we saw here already, and we're now taking the trace over the topologically half-twisted model. And actually, you could also use the full Neveu-Schwarz sector if you so wanted. It doesn't make a difference for the very same reasons that led to this equality here. It doesn't make a difference due to your worldsheet supersymmetry, and that's means that the Q bar here is kind of a little bit of a misleading thing. It doesn't occur on the right-hand side. Everything that, every contribution with non-zero exponent in Q bar actually will cancel out. So that's the definition of the conformal field theoretic elliptic genus. And this expectation here actually does hold in those examples where we can check it, or where we can make it work by definition. We can check it for toroidal conformal field theories. Those are just lattice, essentially lattice VOAs dressed up a little bit. So there, both sides are zero, and they do agree. And then we have a notion of so-called K3 theories. I'm not giving you the definition here. I'm just telling you that, well, essentially you have to use the ingredients that I listed previously for our superconformal field theories, working at central charge 6, so with d equal to 2 here. And for these K3 theories, that equation here essentially holds by definition. So I'm saying we're cooking up a definition of K3 theories, which doesn't have to make use of nonlinear sigma model constructions, and thereby the fact that that equation holds is actually built into the definition. Well, if nonlinear sigma models are well defined, they are examples of K3 theories, so things do fit together here, but I don't need the definition of nonlinear sigma models in order to make things work here. Good. Just as a warning, it's not really essential for this talk, but you could get a little bit over optimistic because up here we observed that the equality of these invariants could be traced back to the identification of these two spaces. And now I'm saying that at least in the K3 context, we can identify these two invariants, where the geometric one is built on the cohomology of that virtual bundle here, which we spoke about earlier, and the conformal field theoretic one is built on the topologically half-twisted model. So shouldn't expect those two vector spaces to agree as well. They don't agree. Unfortunately, they don't agree, and that kind of has some interesting consequences when you want to work on K3 theories in general and discuss their generic properties. But for this talk, it's just an aside. We won't need that observation later on. Okay, so this was my very quick introduction to elliptic genera, and to introduce all the notions that I had in the title of my talk. Next, I have to turn to the singularities that are relevant here. So the singularities that we're looking at will all occur from constructions starting with Calabi-Yau manifold. So again, as before, M is going to be a d-dimensional Calabi-Yau manifold. I'm going to study the quotient by a subgroup gamma of SUD. It has to be a finite subgroup, better act holomorphically and preserve the holomorphic volume form. So altogether, essentially what we're preserving is the Calabi-Yau structure. Then this quotient will in general have singularities, but because I made so many restrictions, the singularities are well under control. We can resolve them, and that's what the twiddle here means. We can minimally resolve them and construct another complex manifold from the quotient, which is then a smooth complex manifold. And actually, by the restrictions that I've made, it turns out to always be a Calabi-Yau manifold. And I call it, just for simplicity, slightly misusing the terminology, I'm calling it a gamma orbifold of M. The case again that will be relevant here is the two-dimensional case, so d equal to 2. In that case, if M is compact, it's going to be a K3 surface or a complex 2 torus. And I will need some intermediate notation where the potentially singular quotient is denoted x0, and its minimal resolution, as previously will be called X. So X then is also a torus or a K3 surface. Now, I mean, this construction of orbifolding, of course, is very reminiscent, and for good reason, very reminiscent of the construction of orbifolding, which I think all of you know in the context of conformal field theory. But still, it's not quite the same. And it's a natural question to ask how these two are related to one another. And I do think that the work that I'm presenting here might help a little bit in confirming what we expected all along, namely a completely close relationship between the two. So for here, all I have to say is that now we have two ways to construct conformal field theories on X. Either we have a notion of associating conformal field theories maybe through a nonlinear sigma model construction, or better mathematically through some mathematical assignment like we have it for the K3 theories. Or you could start with M, which potentially is a little easier, and then take an orbifold of the conformal field theory. And here I'm telling you that on the one hand, toroidal theories are so well under control, and on the other hand, the definition of K3 theories is made for this to work, namely that the superconformal field theory associated to the orbifold agrees with the CFT orbifold of the theory associated to the underlying M. That's really a statement one has to make. It's not automatic, but it holds. And here I'm not trying to sell this as a huge deep result, because we've cooked up the definition of K3 theories so that this is true. So I would just say that we have the right definition here. Good. What does this have to do with the topic of this talk? Well, now we're there because the singularities that can occur in X0 can be shown to be all of this type called simple singularities. So here we now observe the singularities that I want to be studying. I already tried to tell you that we have the elliptic genera, let's say for K3 surfaces and tori very well under control. But now if we have a construction of a K3 surface through an orbifold like this, shouldn't it be possible to understand the various contributions to this invariant by saying which of the contributions comes from the non-singular part of X and which contributions come from the singularities? So it is potentially an interesting question to ask, what do the contributions from each of the singularities look like? And that's the question that Yu Hang solved in his PhD thesis. Good, so to continue, I will say a few more words about these simple singularities. They have a nice ADE classification, and that's almost immediate. If you remember that we constructed all these singularities as such quotient singularities by some finite subgroup of SU2. And these groups are, of course, classified into the cyclic, the binary dihedral, or the binary platonic. And I'm going to attach these labels, AK, DK, and EK, to the various cases here. So these quotients are, of course, singular complex varieties. They all can be described as hypersurfaces in C3, just given by single polynomials. And the translation is stated here. So here are the relevant polynomials that allow isomorphic description of these varieties as hypersurfaces in C3. And these are well known to be actually the simple singularities according to Arnold's classification. So that's why I'm speaking of simple singularities, while in practice, probably I would list an example by saying it's an AD or E-type singularity. And this terminology, which I think is familiar to all of you from Lie algebras, the classification of finite dimensional complex Lie algebras, the fact that this is reminiscent of that classification is of course not a coincidence. It actually is true that the Coxeter-Dinkin diagrams for the root systems of these Lie algebras feature in this singularity story as well. They feature as the dual resolution graphs of the singularities. So what happens here is that I'm resolving the singularity. That's what the twiddle always meant. I'm minimally resolving the singularity that occurs at the origin in that quotient. And just very roughly, that means that I'm replacing the singular point by a curve to get a smooth result altogether at the end. And I can trace back what kind of singularity we've been looking at by looking at what kind of curve I have to glue in. And the curve is called the exceptional divisor. And for these simple singularities, that curve always decomposes into a finite number of irreducible components, all of which are just algebraic curves of genus 0, so just copies of CP1. And the number of curves that you have agrees with the index of the AK or EK that we have here. And these pictures here depict the form of the curve. So for each of the irreducible components, I'm going to draw a node. It's just true that all of them intersect transversally, and if and only two distinct ones intersect non-trivially, then I'm going to draw an edge between the corresponding nodes. And then it just turns out that these are exactly the cartoons that tell you what these curves look like. So you see the familiar ADE-type root diagrams. That's of course helpful when you start calculating with this stuff. Okay, so these are the ingredients to the story. And now let's ask the question that I asked at the beginning again. How can we make sense of complex elliptic genera for ADE-type singularities? First, a little bit of notation to keep things easier. I'm going to misuse the letter gamma or the letters AK, DK, and EK a little bit. Up to now, they denoted the subgroups of SU2, but very often in the following, it will be just the shorthand for this space here, the resolved singular space. And starting from a CFT point of view, for starters, the natural question would probably be, can we associate a topologically half-twisted model so that we can calculate a conformal field theoretic elliptic genus? Let's start with the simplest case where gamma is just a trivial group. So now we're working on C2. And of course, all of you can calculate a topologically half-twisted model on that. That's just a BC beta gamma system where we have two copies of everything because we're working in dimension 2. So here I'm just almost vaguely telling you what the Fock space looks like. I'm introducing, apologies for that, slightly non-standard notation. So the letters here, AN and B, M, K, are going to be the bosonic modes. The phi MK and CNK are going to be the fermionic modes. And I'm flipping the sign in the indices as opposed to what most people do. So here the creators all have non-negative indices, and M is always a non-negative index, and N is always a positive index. So there's a distinction between the A and K and the B MK, which I'm sure you're all familiar with. Well, for the purposes that I have here, I don't need to tell you what OPEs all look like. Anyway, you know that. But what is relevant for the construction of the elliptic genus is, of course, the action of these three guys that I championed previously already, the L0 top, J0, and J0 tilde. And now you see why I'm using this uncommon notation. I do want the index here to give me the energy. So that's what's happening here. Of course, anyone can multiply by -1, so it's not a deep thing. Good, so that's the action of L0 top, and then J0, the U1 current. Okay, the bosons are uncharged, and the fermions have charge +1 or -1 respectively, and then the right-handed guy is just trivial everywhere. And this is all you need in order to write out, well, the would-be complex elliptic genus. Remember, we wanted to use the space of states of the topologically half-twisted model, and then take the trace of this operator. And you immediately see it's ill-defined because everything is degenerate, and the troublemaker is the zero mode here because the zero modes of the B's actually don't change any of the relevant eigenvalues, so you get infinitely degenerate eigenspaces everywhere. Not a problem, because here there's a standard method to fix it, to make something well-defined out of such a degenerate situation. We're just going to work equivariantly. And now you have to choose a convenient action, and here it turns out that it's quite useful to observe that we're working on C2, so GL2C is acting naturally. It has C star as a subgroup, just the diagonal C star in there, and that's nicely compatible with all the OPEs. Here I'm listing for you the action on the modes that are of interest for the construction of our Fock space. And now with this equivariant version of the elliptic genus, you get a well-defined expression. And we can calculate that directly. I'm introducing psi as e to the 2 pi I zeta here, so I get an extra parameter here from the equivariance, and that's the formula I had on the previous page, and then you see this infinite product rising there. And you can trace back all the ingredients. So of course you have the bosonic modes contributing here in the denominator. This is B because n-1 starts with 0, and B had the index M, which was allowed to be 0 sometimes, and here you have the A and K, and upstairs you get the contributions from the fermions. Okay, so you just get that explicitly, and then again you notice that you have produced a quotient of theta functions, where of course you also see that things are ill-defined when theta is 0. That was to be expected. We knew from the start that we have to introduce this equivariance in order to get things well defined. Why is modularity such good news now? Well, because now we can start applying our standard orbifold techniques. I'm now just going through the usual machinery of constructing characters or partition functions of theories through orbifolding by just first projecting onto invariant stuff and then adding other stuffs to make things invariant again. So because we're starting with something that has modular properties, at least on this formal level, that makes sense. And you can just go about and do the calculation, and this is the result that you get. For instance, in the case of AK, because we know precisely how the cyclic group ZK+1 underlying the singularity acts on our space H0C2, and then you just crank up the machine and you get this kind of result. And this formula was known already before. Harvey, Lee, and Morty suggested it as well. They had a slightly different approach. They were working with gauge linear sigma models. For the experts, it's not a surprise at all that we arrive at the same formula, but the motivation and the arguments are a little bit different. Good, we have that. And for the other singularities, it's just a little more calculational work. There's no more technical ingredient that you need. And of course, by the construction, I hope you will not be surprised that, of course, for all of the singularities, the basic building blocks always are these guys here. Just you have to add them up with different multiplicities. So for completeness, if you want, at this point, I'm giving you the formulas for all the other cases, which actually haven't occurred in the literature. And because all the building blocks here agree with those of the AK cases, you should be able to rewrite everything in terms of sums and differences, weighted sums and differences of AK type elliptic genera. And that's what I'm doing here at this point to save space, but later on we will interpret these formulas as well. So why is it that D can be expressed in terms of A, and similarly for E? Good, so I like this, it's nice and explicit, and at least it gives some answer. But you may say that this is a big cheat because I didn't construct anything and I left the geometric world quite early on. I worked on C2 and that was it. And then I used a standard machine of constructing partition function, that is this modular thing. Does this have anything to do with the singularity, or let alone the resolution of the singularity, which I was after, actually? Good question. Let's take a look at the geometric story. Luckily, there's an equivariant index theorem which helps us here, which is made exactly to answer questions like this. We observed previously that the elliptic genus is really an index and can be calculated through one of these integrals. And there's a version of this which introduces equivariance with respect to some group action. It's a classical theorem working on a compact manifold again. We need the action of a compact topological group. G is going to be our favorite element of that group. And then you can twist the index that you're calculating by that group element, but just inserting it into the relevant trace of the heat kernel. And then the final result is this one here. And I don't have enough time, I'm afraid, to go into much detail here. But I hope you can recognize that this is exactly the same form that we had previously for the integral, where I introduced these churn roots to make things more easy to calculate. And indeed, this is really just a generalization of what we had previously. Important point here is that the integral is only taken over the invariant part of the manifold with respect to M, which I'm decomposing into its connected components here. So that's what this means. Actually, everything else cancels out because you have inserted a G into the trace here. So that's something that's also quite familiar from representation theory. So we're only taking the integral over the invariant part of the G invariant part of M. And then the rest of it really looks just very similar to what we had previously. And if you insert the identity for G, then indeed, this all collapses back to the formula we had previously. It sees well, the invariant, the fixed point locus of G, it sees the restriction of the tangent bundle to that fixed point locus and its decomposition into eigenbundles with respect to the G action. I'm labeling this through the respective eigenvalues here. And then you need the total Chern class of each of these eigenbundles here. And those are the Chern roots that feature over here. And you see the G action introduced right here with the zeta L. Okay, so that's the classical theorem we would like to use. Yet, of course, we can't because none of the assumptions are holding in the context that we want. I wanted the ADE-type singularities, which are certainly not compact, not modeled on compact spaces. Also, when I resolve them, it's non-compact. And the group that we were using was C star, it's also not compact. That latter problem is not really a problem because C star contains U1. You can start by making things equivariant with respect to U1, and then you see that it's very easy to extend things to all of C star. And compactness here is not such a huge problem. If you look at the proof of this theorem, you will really see that there's this cancellation of contributions because of the introduction of G here. As long as the integration here is well defined, we're actually home free. As long as the fixed point locus here is compact, one can at least try and apply this formula. So later when we're working on this in this non-compact setting, we won't be able to insert the identity for G. We will have to insert non-trivial group elements, but let's try what we get when we do that path legally. So here I'm just giving you more details for the calculation for the simplest example. That's of course the A1 case. Remember, that's the quotient by Z2. And when we resolve the singularity, the index 1 here refers to the fact that the exceptional divisor just has one single component, just a single CP1, which you see here. We have the C star action, which I introduced previously in the topologically half-twisted model. It's just the diagonal C star and GL2 C, which acts on here, of course. Now, with the formula that I had on the previous transparency, I have to calculate the fixed point locus of psi. I better make things non-trivial, so I'm going to exclude the identity and also -1. Then you notice immediately that on the quotient, nothing is invariant apart from maybe the singular point because, well, psi sits in C star and just acts diagonally on C2, and I've excluded -1 as well. So the fixed point locus can at most be the exceptional divisor here, and it actually is the exceptional divisor. If you've ever done this resolution by hand, then you know that the exceptional divisor here can be interpreted just as the space of complex lines through the origin. When I multiply a complex line through the origin by some parametric psi, the action is non-trivial, but it maps the line onto itself. So actually on the resulting CP1, we have a trivial action, and indeed, this is the fixed point locus. Well, and then you have to push the calculations through. This is a little bit technical, but can be done, and it's not terribly complicated. And then I'm inserting in the formula that we had previously. I have to integrate over this compact thing, introduce the Chern roots like before, and just copy this expression in terms of theta functions, and this is it. With a little bit of help of complex analysis, one can actually integrate this. One can do this, and this is the result. So you see, as you should expect, there are poles here when zeta is 0, for example. Not a problem, we expected that. So that's the formula, and it looks quite different from the one that I had previously by these, by just mechanically applying the orbifold construction to something that looked modular. But actually, one can show that this is exactly the same formula that we had previously. One has to do a bit of a residue calculus, but again, this is standard complex analysis tools, which actually show also in all the other examples, which work similarly, just afford more work. One can show that we have produced the very same formulas that I had previously, where then afterwards I said maybe this was a cheat because I started with C2 and just mechanically did a CFT orbifolding procedure. So we have equality here. Good. good, we have a formula and we feel comfortable with this formula, but I got completely sidetracked from the original task, namely to introduce an elliptic genus on the ADE-type singularities, which I could then include and maybe as a contribution to the K3 elliptic genus. We had to introduce the C star action here and make things equivariant to get something well defined, but definitely this C star action has not the slightest chance to survive gluing into a K3 surface, so it will never be a global C star action on K3. So I cannot really use these equivariant guys in order to implement this into K3. So I better regularize and somehow create a possibility to send zeta to 0 here again. And that can be done. It's inspired by work by physicists who already did something similar. Dixon, Harvey, Waffer, and Witten in this classical paper did something similar just on the level of the Euler characteristic, where they introduced a orbifoid Euler characteristic, which is not integral anymore necessarily, it can be rational. And they introduced it in a way so that the Euler characteristic of an orbifold is computed by taking the Euler characteristic of the original manifold, dividing by the group order, and then adding up separate contributions from each of the singular points. So S here is the set of singular points, and I'm assuming it to be discrete. We can do something similar. We can lift this to the elliptic genus. That can be done by, well, taking our definition of the equivariant elliptic genus and essentially subtracting from it the troublemaker. And you can see that it looks similar to what we have here. That was the motivation to try with this term first, with this construction first. And what we have here is then at the end of the day an expression which has a well-defined limit as zeta goes to 0, and which allows us to extract the orbifold Euler characteristic as well. I didn't say that, but from the elliptic genus, you can always recover the Euler characteristic by inserting z equal to 0, and that holds true here with this orbifold Euler characteristic. And even better, in the case that we're interested in here, that Calabi-Yau two-folds, if M is a K3 surface or a complex torus, and the action obeys all the properties that I listed before, then we have the analog of the formula that Dixon, Harvey, Waffer, and Witten wrote down. We can calculate the elliptic genus of the orbifold by taking the elliptic genus of the original manifold, dividing by the group order, and then adding a separate term, a regularized term for each of the singular points. And here, indeed, this equation says that what I'm writing here is well defined. We get finite results over here all the time. Good, so that was the task for that thesis. And then in passing, we noticed this formula that I pointed to you earlier, namely that it's kind of intriguing that the D singularity can be expressed in terms of A-type singularities, but here there's a minus sign. What is that supposed to mean? And we had similar formulas in the cases of the E-type singularities. And here the geometric interpretation of this formula I find quite pretty, and that's why I would like to share it with you, though probably, I mean, our observation is probably not very deep mathematically, but I think it's reassuring, and it also works as a reality check, and it forces me to cite this beautiful work by Sludovi, which is very deep and deserves to be cited here. Sludovi, among many other things in the 80s, discussed how to, discussed the setting where you construct orbifolds quotient singularities stepwise. So whenever we're quotienting by some group and it has a normal subgroup, I could attempt to first take the quotient by the normal subgroup and then blow up, have an induced action of the quotient of these two groups and go through the same procedure again. And he essentially proved that that is legal. The final result is the same thing. So you can make complicated group actions easier by carrying them out stepwise, maybe one could say. And here for us, the crucial observation is that all the groups that we need contain a normal subgroup Z2. And it all goes back to the case of A1, where we first divide the group Z2 and produce a A1 singularity, like here, And then there's an induced action on the resolution of the quotient group, and then you divide by that and continue to construct the original singularity like here. So for dk plus 1, the red dot here denotes the exceptional divisor of the blow up of the A1 singularity here. We've seen that before. And then we have a group action which happens to produce 3 fixed points, all give singularities of ADE type, and that's how these 3 legs arise. But not just like that. Actually, we have to keep in mind that we're working on Z2 covers all the time here, and when you go through the details, that explains why we have these half factors in front. Actually, this leg here arises from an A3 singularity, where if you look at the Oxford-Dinkin diagram, you fold it in the middle. You fold it in the middle, and the middle point, which is now counted double kind of, is glued head-on onto this red dot here. And similarly for that leg, you might have guessed it's an A1. No, it's half an A3. And this leg is also half an A whatever, so that the indices match. And that explains the formula, because we have 1/2 of the big AK, and we have twice 1/2 of A3, so that's why we have the prefactor 1 here. And now we have to correct for overcounting, because we added half an A1 from each of the legs. That's 3 halves. That's too much. That's a half too much, because there's only 1 A1 in the middle, and that explains that guy at the end. Yeah, that's a bit hand-wavy, but we have the formula and it holds, and all the, the group actions and so on. We can go through that in detail. Plus, it also works in all the other cases. E6 here, again, we have the central A1. Here we see half an A3, half an A5, another half A5. Yeah, 2/2 A5, 1/2 A3, correct for overcounting. E7, central node, half an A3, half an A5, half an A7, confirmed, correct for overcounting. And E8, well, that is just the same again with slightly different indices. So for me, this was a reality check. And again, you can go through all the details in quite some, with full precision. I think I went over time already, so thank you for your patience. And that actually was the end of my talk.
Do we have any questions?
Hi, thank you for the talk. I was wondering, for all this story, it was very important that you have this n equals 2,2 supersymmetry. So is there something analogous if you demand less supersymmetry so that your target space is not Kähler, for example?
I don't really know. We're currently investigating whether there's something similar on the geometric side in the G2 context. So for G2, of course, we still have special homonomy, so you might expect that similar effects hold. And also there's beautiful work by many people in the audience at the moment about chiral complexes associated to this situation. But how to cook up an invariant similar to the elliptic genus is not clear at all, because, well, if you look at indices of the Dirac operators there, you can do it, but it's all 0. So that doesn't give you much structure. And that seems, it's again a PhD project I'm supervising together with my colleague Sebastian Goethe in Freiburg. This is Jonas Lento working on this. And we have some preliminary results. So there seems to be an unexpected connection to the new invariant. And so yes, my answer has to stay vague because the work is not finished. But yes, I think there are similar things in other situations. But here, as you observed, I'm really working very, very concretely with all the supersymmetry that I have. And it is quite crucial to make things work.
Yeah, no, that's very interesting. Yeah, thank you very much.
Any other questions, comments? Anything on Zoom? If not, let's thank the speaker again, and we'll resume after lunch.
Thank you. Bye-bye.
Thanks, Catherine.
Thanks so much.